Hi, I'm Professor Melko, Chemistry PhD, and your university chemistry professor. Today we're going to talk about balancing reactions, classifying reactions, the activity series, and solubility rules. But first, periodic coffee. All right, now I'm ready. Let's get started. So today's a practice problem video. We're going to start with balancing chemical reactions with this example. For nitrogen gas reacting with hydrogen gas to produce NH3 gas, what is the coefficient of NH3 after balancing this reaction? So this was actually a very important reaction known as the Haber-Bosch process to perfect this, and really went a long way in the world wars. But that's a different discussion for a different day. Let's try to write and balance this chemical equation. As always, we start by identifying what the species are. Nitrogen gas. We remember nitrogen here in the periodic table as one of these diatomic gases. So this is always going to be written as N2. This is reacting with hydrogen gas and hydrogen, another one of these diatomic gases. To produce means arrow, separating the reactants, nitrogen gas and hydrogen gas, from the product, which here is ammonia NH3 gas. So I'm writing all the states of matter as well. So we have nitrogen gas plus hydrogen gas making ammonia. As always, I like to keep track sort of separately here on the left and right, the number of atoms of each, N's and H's on the left, N's and H's on the right. On the left, I have two nitrogens, right? Two atoms of nitrogen in this one molecule of nitrogen gas. And similarly, two atoms of hydrogen in this one molecule of hydrogen gas. On the right, the 1 is sort of implied. For nitrogen, there's no subscript, so I know it's a 1. And the 3 for hydrogen tells me there's 3 of these. Great. I can look at nitrogen here. See, there's 2 on the left, 1 on the right. And I can increase this 1 on the right to match the left, making it a 2, by putting a 2 in front of ammonia. Notice I don't change the subscript, never change the subscript. That changes the molecule. I still want it to be ammonia, so I just leave it as NH3. But I can put this 2, written quite poorly here, out in front to change this 1 to a 2. So now my nitrogens are balanced. But doing so, make sure you're updating the other part of the molecule, hydrogen. You've now changed that from 3 to 6. You've doubled it. So now, although my nitrogens are balanced, my hydrogens are not. 2 hydrogens on the left, 6 on the right. So I need to update this to a 6 on the left by placing a 3 out in front of hydrogen. So as always for balancing chemical reactions, first make sure we get the formula right. We did that. Count up the number of atoms on each side and start writing coefficients to make sure the atoms of each are balanced. And then at the end, of course, make sure you're going back and double checking after you balance the reaction that the atoms add up on the left and right appropriately. So just at the end here, my coefficient in front of nitrogen is a 1. There's 2 atoms on the left, 2 atoms on the right of nitrogen. Hydrogen, 6 on the left, 6 on the right. So this looks good to go, and that is fully balanced. Let's try another practice problem. As always, feel free to pause the video here and try this for yourself, as I'm going to go ahead and work through it to show you. But it's always best to practice this. Even if you struggle, go ahead and give it a try. You'll learn much more if you struggle, fail, and then see how it's done rather than just watch the video. In any case, let's balance this reaction. A lot of big words here that we need to break down into these chemical formula. Right? So that's step 1, as always. Try to write down what each of these are in symbols. Okay, the first is lead 2 nitrate. And we learned about Roman numerals in past videos. If you're having trouble naming these, go back and watch my previous videos. If you're having trouble balancing, go back and watch my previous videos on how to step-by-step balance reactions. This video is just about working through some practice problems. For lead 2 nitrate, lead I've learned is Pb. And this 2 tells me that the charge on lead is 2+. Nitrate is a polyatomic. Maybe you've memorized it, maybe you need to look it up in the polyatomics table. Either way, you can find nitrate in that table as NO3 1-. Now, because these charges don't match, okay, if it was 2+ and 2-, then it'd just be a 1-to-1 ratio of lead and nitrate. But since lead is twice as charged as nitrate, I need to account for that in the chemical formula. So this 2 on lead becomes a subscript 2 on nitrate. and the 1 on nitrate becomes a subscript 1 on lead. And again, I don't write the 1 subscript, it's just implied. So my formula for lead nitrate here looks like so, remembering to use parentheses around nitrate to make sure there's 2 whole units of nitrate in this lead nitrate formula. So that's my formula for lead nitrate, and it's aqueous. I want to make sure I keep track of these states. And it's reacting with potassium iodide. Potassium, K plus 1. Iodide comes from iodine, the element, minus 1. That's a 1-to-1 ratio, so this is quite straightforward. The formula is just Ki. These produce, so draw the arrow, separating reactants from products, solid lead 2 iodide. Going through this naming the same way, sort of like we did lead nitrate, you should get this 2-to-1 composition to make sure the charges balance. And I'm told it's solid. That's where the S comes from in the state of matter. So lead iodide and aqueous potassium nitrate, which we should be able to write as KNO3. Great. So now I have everything written. I can go through and balance. At the end, I'm going to answer what is the coefficient in front of lead 2 nitrate. So again, separate left from right here. I want to balance lead. I want to balance nitrates, right? These polyatomics, if they appear on both sides, I'm going to treat them as a singular unit. So there's nitrate on the left, nitrate on the right. I'm going to treat that as a whole nitrate unit. You can separate it out, it's just easier to do it as one whole unit. Potassium iodine. So I'm going to keep track of each of these. Just separating reactants from products here. So let's see, on the left, lead, there's 1 of them. Nitrate, there's 2 of those. Potassium, 1, iodine, 1. On the right, lead, there's 1, iodine, 2, nitrate, 1, potassium, 1. So there's some imbalance here. To start balancing, I always start with the most complex species. So the polyatomic in this case, nitrate, is where I'm going to start. NO3, there's 2 on the left, 1 on the right. So let's make this a 2 on the right to match by placing a 2 coefficient out front. Doing so, I also notice affects potassium, brings that up to a 2. And now that my nitrates are balanced, I see that my potassium is not balanced. 2 on the right, 1 on the left. So I'll add a 2 coefficient in front of potassium on the left to update that. Doing so also changes my iodine on the left and makes it 2. But conveniently, there's iodine that is 2 on the right, so now those are balanced, potassium's balanced, nitrate's balanced, and lead I don't have to do anything, it was balanced to begin with. So, double checking, I've written everything, correct formulas, correct states of matter, and everything should balance. Lead, 1 and 1, nitrate, 2 and 2, potassium, 2 and 2, iodine, 2 and 2. So this looks fully balanced. The coefficient in front of lead nitrate, it's implied there, it's a 1. So in the balanced equation, lead nitrate gets a 1 out in front. That would be the answer to this question. Moving on. We've also talked about in past videos classifying reactions. Things like single replacement reactions sort of depend on the activity series, whether things will replace other things, right? Whether one metal can replace another metal depends on how active it is. And we have this activity series at the bottom that explains what metals are more active than others. So lithium the most reactive, gold the least reactive, and shown in series here. So to answer these types of questions, we consult the activity series. Cadmium foil is put into a lead 2 nitrate solution. You don't have to write everything out here, but if you wanted to, it would look something like this. Cadmium solid plus lead, and we just balanced lead 2 nitrate on the previous slide. It would look like this. Does a reaction occur? So a reaction occurs if cadmium can displace lead. This is a single replacement reaction, which means I consult the activity series. Does cadmium come before lead in the activity series? Here is cadmium, here is lead. Cadmium is before lead, so yes, reaction will occur, and I'll knock lead out and replace it with cadmium. So yes, the answer here is reaction will occur. You don't really have to write out and balance the chemical reaction. You just are comparing cadmium is before lead, so yes, reaction will occur. Cadmium is more active. Likewise, we can try the second one here. Zinc, Zn, dropped into hydrochloric acid. So in these types of problems, remember, consulting the activity series, we're not so concerned with chlorine, that's the anion. It's whether zinc can replace the cation here or hydrogen. So does zinc, shown here, come before hydrogen, shown here? The answer is yes. Zinc's before hydrogen, so yes, even here, reaction will occur. So the H here in the activity series is sort of the placeholder for all acids. Metals that come before acids will react in acid. Metals like copper, silver, mercury, and gold do not react in acid via single replacement. So the answer for both of these should be yes. That's single replacement reactions. We can also think about double replacement reaction. And for those, we consult the solubility rules. So here's a table, right, of solubility rules, whether things are soluble or dissolve in water. If they do, right, they make these aqueous states. If they don't and they're insoluble, they form precipitates or solids that we signify with parentheses S. In all double replacement reactions, reaction occurs if one of the products is insoluble, aka a precipitate, aka a solid. So we use these solubility rules in double replacement reactions to predict will a reaction occur, kind of like we use the activity series in single replacement reactions. For double replacement reactions, one of the products must be insoluble for us to say yes, reaction occurs. Otherwise, everything's just fallen apart and dissolved into ions floating around in solution. There is no net chemistry happening. So we would write no reaction occurs if all of the products are soluble. So this is just a more straightforward question. Are these substances soluble in water? The first, BaSO4 barium sulfate. We can read through here and see that the sulfate anions appear here. They're always soluble unless it's lead, barium, or strontium with sulfate. So when barium's paired with sulfate, it is no longer soluble, so this would be insoluble. Barium sulfate is not soluble in water. It's insoluble. For aluminum nitrate, here's nitrates. They're always soluble, so the answer is yes. It doesn't matter what's paired with it. It happens to be aluminum, but in this case, nitrate, definitely soluble, so that's a yes. Finally, we're going to work through classifying reactions. We have 5 different types of reactions: combination, decomposition, single replacement, double replacement, and neutralization. Okay, combination reactions, couple things coming together to form one product. Decomposition, one thing falling apart to make multiple products. Single replacement and double replacement, exactly what they sound like. An element and single replacement replacing another element. In double replacement, 2 elements switch places. The cations trade anion partners. And neutralization is an acid plus a base, making water and a salt. So let's classify these reactions. The first one, there's one item on the left, falling apart to multiple things. That's decomposition. One thing that is decomposing and making multiple products. The second one, when H is out front, sort of looks like an acid. OH group, frequently a base. We also notice that water is formed, right? Characteristic of a neutralization reaction. So acid plus base makes a salt plus water. That's neutralization. So neutralizations will always have water as a product. But you should also be able to identify it by an acid plus base on the left. The third one here, copper metal heated with oxygen produces solid copper oxide. right? We can write this out as a chemical reaction. Copper metal, so that's a solid. Oxygen, that's one of these diatomics, O2 gas, produces solid copper 2 oxide. Since oxygen is -2 and copper is +2, it's a 1-to-1 ratio. Right, so we can even balance this thing like so to write out. Maybe it makes it easier for you. So, we have an element plus a gas. Might look like single replacement, but there has to be multiple products. Here it's only one product, and if there's only one product, that's combination. Okay, so this is multiple things coming together to make one product. That's combination. Finally, aluminum metal reacts with aqueous manganese sulfate to give aluminum sulfate plus manganese metal. Okay, this, spoiler alert, single replacement. I can identify that pretty much immediately just through reading through. I see I have an element reacting with a compound, and it yields a different element. So one element is replacing another. Aluminum is taking the place of manganese to make aluminum sulfate. So that's single replacement. Right? If you wanted to write it out, aluminum solid plus manganese sulfate makes manganese solid plus aluminum sulfate. And you can go through and balance this if you really care to. I guess this would be here, 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 and that should be good. Yep. So that's classifying different reactions. We had decomposition and combination, which are sort of opposites. Neutralization, which features water on the right, acid plus base on the left. Single replacement, a single element kicking another one out. Double replacement, not shown here, would just be a compound, not an element, written here, that's trading places with another element in a separate compound. So that does it for practice problems here. As always, you can find more videos like this and practice problems on my YouTube channel. Feel free to subscribe. And every week I have office hours over on Twitch, where we talk about science news, do practice problems just like this, and answer whatever chemistry questions you might have. That'll do it for today's video. See you next time.